Hello everyone. Today I will give a talk about improved small-gain conditions for input to state stability with respect to measurement functions for discrete time networked system. In this talk, I will characterize small-gain conditions for input to state stability with respect to measurement functions, omega ISS, of distributed algorithms. The small-gain theorems are based on the dissipative form finite-time Lyapunov function, and they relax the assumptions in some other papers. The theorems can be applied to distributed algorithms such as mean or max consensus, biased mean consensus, and etc. under additive errors. This page demonstrates the notations used in our paper, including the set of real numbers, the set of non-negative real numbers, the set of integers, and the set of non-negative integers, the Euclidean norm, the supernorm, and the set of functions with finite supernorm, and the comparison functions such as class kappa function, class kappa infinity function, and class kappa L function. We consider the following on discrete time networked systems. In this networked system, the state of the subsystem I at time k+1 depends on all subsystems states in the previous round and the input uk. Therefore, the composite systems can be described as shown in equation 2. The f(i) function in equation 1 and the f function in equation 2 are both continuous. We first give the definition of measurement functions. We call omega a measurement function if it is continuous 0 at 0 and negative otherwise. Next, we introduce the definition of global k-boundedness. Given a measurement function omega, we say the f function in equation 2 is globally k-bounded with respect to omega if there exists two class kappa infinity functions v1 and v2 such that for all the initial condition xi and all the inputs u, the omega of the f value is upper bounded by the summation of v1 of omega of xi and v2 of the Euclidean norm of the input. The continuity of the f function that we have assumed guarantees its global k-boundedness, which is also a necessary condition of omega ISS. Now we formally give the definition of omega ISS. Given a measurement function omega, we say the system 2 is omega ISS if for all initial condition xi and the input and all the integers k, we have omega of the state at the kth time step is upper bounded by either beta of omega of xi and k or lambda of the supernorm of the input. Here the beta function belongs to the class kappa L function and the lambda function belongs to the class kappa function. Now we turn to the definition of dissipative form finite-time Lyapunov function, DFTF. Given a measurement function omega, consider the system described in 2. A continuous real-valued function v is called a dissipative form finite-time omega ISS Lyapunov function for 2 if the following two conditions hold. First, there exist two kappa infinity functions alpha 1 and alpha 2 such that for all the initial condition, v of xi is lower and upper bounded by alpha 1 of omega of xi and alpha 2 of omega of xi, respectively. Further, there exists a positive integer m and a positive definite function alpha dissipative such that id minus alpha dissipative belongs to the kappa infinity function and a lambda dissipative function belonging to the kappa function such that for all the initial condition and all the input, the V of the state at the mth time step is upper bounded by the summation of alpha dissipative of V of the initial condition and lambda dissipative of the supernorm of the input. According to previous results, the system 2 is omega ISS if it admits a DFTF. Further, if we set the integer m in the second condition to be 1, then DFTF reduces to the classical dissipative form Lyapunov function. Then we introduce the two main functions used in our paper. In the first assumption, for any subsystem I, we assume there exists a measurement function omega I and a continuous function vi such that for any initial condition Gzi I, vi of Gzi I is lower and upper bounded by alpha underline I of omega I of Gzi I and alpha bar I of omega I of Gzi I with alpha underline I and alpha bar I belonging to the kappa infinity functions. Further, we assume there exists a positive integer m and a positive integer l which is greater than or equal to m, a constraining subsystem IL which belongs to the set of neighboring subsystems of subsystem I, a state comparison function lambda IL belonging to the union of a class kappa function and a zero function, and an input comparison function lambda IUL such that for all the initial condition Gzi and all the input u, vi of the state of the subsystem I at the lth time step is upper bounded by the summation of lambda IIL of VIL of the state of subsystem IL at the L minus mth time step and lambda IUL of the supernorm of the input. Further, we assume the comparison function lambda IIL in equation 8 is subadditive. With the state comparison function, now we define a L by L GAN matrix gamma, such that the ith row and jth column element gamma ij obeys gamma ij equals to lambda ij defined before, if j is a neighboring subsystem of subsystem I. Otherwise, gamma rj is equal to zero function. This GAN matrix further defines the map gamma circle plus, which obeys this equation. With this definition, we introduce our second assumption. In assumption 2, we assume all the cycles in the gamma circle plus operator are contractions. So lemma 1 is a technical result based on assumption 2, which says that if assumption 2 holds, then there exists a vector of class kappa infinity functions such that gamma circle plus of sigma of s is strictly less than sigma of s for any vector of real values greater than 0. Now we give our two theorems. Theorem 1 says that if assumption 1 and 2 hold and the sigma function defined before is subadditive, then the system 2 is omega ISS. By assuming sigma is subadditive, we avoid the strong Small-GAN condition used in other papers. Our second theorem says that if only assumption 1 holds, and suppose there exists positive integers p such that the composition of a sequence of p state comparison functions is strictly less than the identity function, then the system 2 is omega ISS. In equation 11, IM plus subsystem IM plus 1 and the state comparison function lambda IM plus 1 are the constraining subsystem and state comparison function of subsystem IM in the Kp minus m times time step. Now we look at the applications of the theorem. We apply the Small-Gain theorem to an adaptive Bell-Manifold algorithm, which is an adaptive version of the classical Bell-Manifold algorithm used to find the distance of each node from a set of sources in a connected graph G. According to Bellman's principle of optimality, the true distance of node I, di, obeys this recursion. In this recursion, n of I is the set of neighbors of node I. Eij is the edge length between node I and node j. S is the set of sources. Here we call the minimizing j the true constraint node of node I. Mimicking this style, we define our ABF like this. In this recursion, d hat I of t plus 1 is the distance estimate of node I at time t plus 1. And here, epsilon I of t is the additive noise caused by measurement errors at time t. And similarly, we call minimizing j here the current constraint node of node I. And then we define an important parameter d of g, which is the effective diameter of the graph, defined as the longest sequence of nodes where the predecessor of each node is one of its true constraint nodes. According to our previous result, d of g is finite. Then our first lemma shows that if we define the state as the distance estimation error and the input as the additive noise, then by defining vi as the Euclidean norm, we find that vi has the similar properties as we defined in assumption 1. Here, lambda ij is less than or equal to the identity function, where the equality holds if j is the true constraint node of node I. Then, as d of g is finite, ABF is omega ISS by using theorem 2. Here, d of g functions as the positive integer p as defined in our theorem 2. Here is the conclusion. Based on DFTF, we give two small-gain theorems for omega ISS for discrete time network systems. Those theorems relax the conditions in previous results, and we apply the theorems to the adaptive Bell-Manifold algorithm, proving its omega ISS. Thank you.